moment distributions. So what is moment distribution? So I say that moment distribution is a shortcut version of the slope deflection. So previous chapter we spent a lot of time talking about slope deflections, which seems to be a very powerful approach that can help you to solve indeterminate structure. The advantage of this slope deflection approach is it's not directly tied up with a degree of indeterminacy. As we say that the indeterminate structures tend to have a very high degree of indeterminacy. So if you tie up directly with degree of indeterminacy, then you end up something that you cannot solve. So slope deflection, turn around, look at the deformations, and try to identify so-called degrees of freedom. So of course, the underlying assumption is the degree of freedoms will be much, much less than the degree of indeterminacies. Right? So that you can solve your problems much more easier. Now, moment distribution is one step further. It's trying to further help you to simplify the analysis. So let's revisit the slope deflection methods here, and then go on from that methods to moment distributions. So basically, we have a four-step procedure for slope deflection methods. First, you identify degrees of freedoms. So the degrees of freedoms are deformations, rotation angle, or rigid body rotation angles. Right? And rigid body rotation angle can be related to displacement of the structure. And then you set up components, and then you write n moments of the components. And n moments of the component can be related to degrees of freedoms, which is deformations of the structures. And then you try to set up equations at the joint. So the joints are defined as the connections between components. So you set up degrees of freedom, you solve degree of freedom using equilibrium condition you set up at the joints. And then you back substitute into the previous step force deformation relationship. Then you can obtain forces from the degrees of freedoms that you solved. So this is pretty much the slope deflection approach. All right, so let's illustrate this slope deflections methods using this example, and then start to inject the idea of moment distributions. All right, so this is a beam, hinge support, and then clamp here. And assuming that they have properties of EI and L, so EI, L could be different between the two span. And this is a slope deflection equations that you can use to solve this structure. And I apply an external moment, counterclockwise moment at joint B. So I wanted to solve this structure using slope deflection. First of all, identify degrees of freedoms. So degrees of freedoms is rotation angle here, and then rotation angle here, but you also identify that this is a clamp boundary conditions, so rotation angle should be equal to 0, so you end up with 2 degrees of freedom. So you'll be anticipating that you need to solve these 2 degrees of freedoms using 2 equations. So here you go. We break them into components. So this is a component AB, component BC, and then they are connected at joint B. So you put down n moments, MAB, and we say that we follow particular signs conventions. My sign convention is counterclockwise positive. So bending moment, MAB, but it turns out this is a moment-free end, so MAB should be equal to 0. Here you go. That's the first equilibrium conditions that you can use. On the other end is MBA. So MBA, again, follow the sign conventions, counterclockwise to be positive, and this is just action-reaction, right, acting on joint B. So that's MBA. And then go to component BC, you have MBC, and then you have MCB. Now all of these M moments can be established using slope deflection equation and can be related directly to the degrees of freedoms. So here you go. We set up one by one, strictly follow slope deflection equations. Now this is a fixed end moment which is accounted for the external loads acting on the components. In this case, we don't have external loads acting on the components, so the fixed end moments are all equal to 0. So here is a MAB expressions related to degrees of freedoms. It turns out that it's equal to 0, so that indicating that there must be some relationship between rotation angle theta A and theta B. So here, in order to force it goes back to 0. Now how about MBA? Just follow this equations. It's 2EI AB over LAB, and then 2 times theta B times 1 times theta A. And then you can substitute theta A, theta B relationship in it, and then it can be further reduces to 3EI AB over LAB times theta B. Right? Simply just substitute this in here, simplify, then you get that. Now, for simplicity, we call this stiffness coefficients KBA. So we just replace this with KBA for simplicity. All right, similarly, MBC. MBC is 4EI BC over LBC times theta B. And again, for simplicity, we just express 4EI BC over LBC with KBC, stiffness coefficient BC. And then MCB is 2EI BC over LBC times theta B. Okay, so next step, joint equilibriums. So joint equilibrium requires you at joint B, you need to have MBA plus MBC equal to the external applied moments of M. Alright, so you just take these equations plus that equations and set that equal to M. Then you can get theta B. So you solve for the degree of freedoms, theta B. So that's step number 3. And then step number 4 is back calculating, taking theta B, substitute them back into each individual n components, then you can have all the n moments solved. So we do it one by one. Now this one you don't have to worry. So this one you just take theta B, substitute it into this expression. Then MBA is equal to KBA over KBA plus KBC times M. So this is a coefficient. It's a function of stiffness coefficients KBA and KBC. And stiffness coefficients, they are functions of material property and length of the components, right? So KBA is equal to that. KBC is equal to that. So after you obtain KBA, KBC, then you have this factor. This factor is called distribution factor BA. Notice that I have this subindex aligned with the n moment. So MBA is equal to distribution factors BA times M. Now similarly for BC, so you take theta B, plug it in here. So it's going to be KBC times theta B, which is this. So then KBC is equal to, MBC is equal to KBC over KBA plus KBC times M. Again, I call this factor distribution factor BC. So you can see that the whole calculations, after we've gone through the slope deflections approach, the calculation becomes, if you want to solve for the n moments, it's purely just taking the moment, apply moments, and time some coefficients. which depends on the material property as well as the span width. So distribution factors DFBA and DFBC play a very important role in this calculation. So if we don't care really much about the deformations, we basically can skip all the steps in the middle and then directly goes to calculating distribution factors and then taking distribution factor multiplying by the external bending moments, and then you have the end moments. Right? So you can skip all of these. If you know how to formulate distribution factors, you can simply just formulate that and then substituting them in here and then get MBC, MBA. So you don't need to solve equilibrium equations, simultaneous equilibrium equations, if you just want to find the end moments. Okay, so that's why I say this moment distribution is a shortcut of the slope deflections. Basically, we're doing the same thing, except that moment distributions, if I don't care about rotation angle, if I don't care about rigid body rotations, I can directly formulate the so-called distribution factors and then multiply by external moments and then get the end moments very quickly. Now, to further go on, I summarize the three concepts for moment distributions. The first concept is just what we have described, called moment distributions. That process applies at the joints. And if you have external forces applied on the components, you might need to convert those loads to joints. So that's the first concept, called moment distributions. And then moment carryover. So from one end of the components to the other ends of the component, what happens? Well, you can, like in the previous example, you can calculate end moments here. But how about the end moment at the other ends? So we can use a concept called carryover. We'll talk about that shortly. And then the last concept is claimed and unclaimed approach. So we will explain that further in detail. Okay, so let's go back to this examples and then try to summarize what has happened here. So we identify that moment here should be equal to 0. And moment BA is like that. Moment BC and moment CB. So we go directly to formulate distribution factors for this moment, for the intentions that we want to directly distribute this moment by taking that moment multiplied by this distribution factors and then set that equal to MBA. And similarly, MBC is finding the distribution factor BC. Take that, multiply by the external bending moment. Then that should be equal to MBC. So what is distribution factor? Distribution factor is formulated based on stiffness coefficients. So KBA and then KBA plus KBC. So this is the stiffness coefficients here, and this is the stiffness coefficients here. So you have a stiffness coefficient from component BA and then stiffness coefficients from component BC. Similarly, DFBC is stiffness coefficient here divided by the summations of stiffness coefficient here and there. Okay, so what is stiffness coefficients? As we just analyzed in the previous slides, stiffness coefficients is 3EI over L for this component. And stiffness coefficients for this component is 4EI over L. Why there's a 3EI and there's a 4EI? We have to go back to the previous slides to understand what happened. How come one is 3EI, the other is 4EI? All right, so we follow the derivations. What happens? The stiffness coefficients turn out to be different. This is what happens. This end is moment-free. So there's a relationship between this rotation angle and that rotation angle. Okay, so you force this relationship to occur at the end moments at the other ends, and then you substitute that relationship, that gives you 3EI over L. Now, so that explains why this component, the stiffness coefficient here, is 3EI. It's actually triggered by this moment-free conditions there. Right? So because this is moment-free, there's a relationship amount between the angles of the two ends, substitute in, and then it reduces to 3EI. Now, how about 4EI? 4EI, because that end, we don't have a moment-free condition to use. So there's no way you can reduce or you can amend this coefficient because there's no moment-free condition that you can use. So that remains 4EI. Okay, so that explains why one component is 3EI over L, the other component is 4EI over L. All right, so here. So the conclusion here is whether the stiffness coefficients K here is 3EI or 4EI actually depends on the so-called far side conditions or far end conditions. If the far end condition is moment-free, then the stiffness coefficient is 3EI. If, on the other hand, the far end condition is claimed, then the stiffness coefficients remain 4EI over L. So whether you should use 3EI over L or 4EI over L for your stiffness coefficients depends on what is happening at the other ends of the components. All right, so throughout this chapter, you don't have any other stiffness coefficients that you need to worry about. Only these two stiffness coefficients. One is 3EI over L. The other is 4EI over L. And again, it's depending on what is happening at the other sides of the component. All right. Finally, we should also notice that the summations of the distribution factor should be equal to 1 at the joint, because you are distributing the moments according to the distribution factor. So summation distribution factor equal to 1 is implied joint moment equilibrium. Right? So in other words, if I know this distribution factors, let's say this is 0.6, then the other must be 0.4, because sum up equal to 1. Now, how about multiple components? Well, it's the same thing. You just extend it into multiple components. So let's say I have a beam like that, hinged, clamped, and then in the middle of the beams I have another components connecting, and then the far end is hinged. I give you the property EIL, EI over EIL, and EIL. Apply a moment at the joint here. So can you analyze the structures using moment distributions? All right, it boils down to starting by calculating distribution factors. So here are the end moments for each component. I have AB component, BC, and BD components. And then I should see 3 end moments at joint B. Now, the reason I plot this clockwise is because they are acting at the joint. at, if you want to plot acting at the component, it should be counterclockwise positive. All right, very quickly, without going through setting up slow deflection equations, if you want to use moment distribution, the first step is to calculate distribution factors. So you should have distribution factors BA, distribution factor BC, and then distribution factor BB. They can be formulated following this. So at the bottom here should be the summations of all three components' stiffness coefficients, KBA, KBC, KBD. On top, depends on where you are. If you are talking about AB, so it should be KBA. If you're talking about BC, KBC, BD, KBD. Right, so that's distribution factors. Now how about K? Stiffness coefficients. As we just said, there are only two stiffness coefficients that you can use. One is 4EI over L, the other is 3EI over L. And whether you use 4EI over L or 3EI over L, depending on the far end conditions. So, very simply, here, KBA is 3EI over L. The reason for that is the far end is a moment-free conditions. Okay. KBD, again, is 3EI over L. The reason, the same. The far end is a moment-free condition. KBC is 4EI over L. The reason is because the far end is clamped. Okay, so that's it. So you use these three stiffness coefficients, substitute them in, then you can calculate distribution factor for all three components. And then you directly take the external moments here, and then multiply individually, and then you get the end moments of the components. Isn't that nice? Very easy, right? You don't need to worry about the if you don't want to know the rotation angle. That is a more direct way to get the end moments. Now, that's the first concept, distributions. Now, the second concept is called carryover. So now you have the moments here distributed. How about the moment here and moment there? Well, moment here is very easy because this is moment free. So there's nothing you need to worry about. Whatever you get there is not affecting this at all. Right? Now, how about moment here and then there? Are they related? Indeed, they are related. If you go back to the previous slides, MBC is 4EI over L times theta B. MCB is 2EI over L theta B. So you can see that one is 4EI over L, the other is 2EI over L. So they are related. They are related by a coefficient, 0.5. It's not negative 0.5, it's positive 0.5. So it's telling you that whatever you obtain here, you just multiply that by 0.5 and then put it on the other side of the component. Very simple, isn't it? So all you need to do is just take that, multiply 0.5, put it there. Same direction. And on the other side, again, you don't need to worry about it because this is moment free. There's no moment there. So you don't need to worry about whatever you obtain there is going to cost you anything on the other side. So this is called carryover moment or moment carryover concept. All right. And then we go to the third concept called clamped and unclamped conditions. Now, just now, the example that we showed, is an end moment applied, is an external moment applied at the joint. Quite frequently, you don't see that. You actually see loading applied at the components. For instance, I have a concentrate load applied here. And if you want to use the slope deflection, of course you follow the procedures. But now I want to see whether I can use the moment distribution approach. So if the loading is applied at the joint, you know how to do it. So the clamped and unclamped concept is trying to help you to get the effects of loading from the components to the joint. So how do we do that? So this is what we can do. We can assume that at joint B, the boundary condition is clamped. So external load applied at component BC, assume this is clamped boundary conditions, then we can calculate this MBC. So this MBC can be obtained using slope deflections. Right? This is a lookup table. This is from lookup table, and then because this is clamped, so rotation angle equal to 0, rotation angle equal to 0, no rigid body rotation, so all of these cancel. Only fixed end moment remains, and then fixed end moment can be obtained from lookup table. So we can get MBC from the lookup table. Also MCB. Now, however, this clamped boundary condition is not supposed to be there. It's assumed condition. The assumed condition induce end moments of NCB. So what you can do to remove the clamped boundary condition is to apply a counterbalance moment there. So if I get a moment counterclockwise, I apply a clockwise moment. So when I do superpositions, you see that these two moments is going to be cancelled and only loading remains. So you go back to the original loading conditions. So by doing so, you can achieve the purpose of converting the loadings acting on the components to the loading at the joints, which is quite clever. So basically following superposition concept. Clamp it first, calculate the end moments, and then apply backward, trying to cancel that. And then from this point onward, it's the same as before, the previous example. You can directly distribute the moments into the component and then carry it over to the other end. Right? So basically, this case plus this case equal to the original case. And this case is simply just following slope deflections. And in this particular case, it's just following the lookup table. All right, so for that nature, we call this fixed end moment. So this is a fixed end moment in the moment distributions. All right, so how about a condition like this? Now, apparently, this is a joint moment applied at A. This moment is going to create structure to deform like this. And there will be moment here and moment there. So how do you analyze this behavior using moment distribution? So how much moment will be carried over from here to this end of the components? Right? From one end of the component we call moment carryover. So you look at this end. This end is not free. It's not moment free. It's not clamped. It's actually somewhere in between. Somewhere between free and clamped. So how do you carry over moments from this end to the other end? You cannot. Because if this is clamped, you carry over 1/2. If this is moment free, you carry over 0. But this is not, it's not free, it's not clamped. So what do we do? Well, you can use the concept again called clamped and unclamped approach. So what you can do is you assume that this B is clamped. And because of this clamped assumptions, you are allowed to carry over 1/2 to the other side. Right? So that is 0.5 times A, carry over to that side. And then this claim boundary condition is not supposed to be there. So what you do is you further then counterbalance that moment appear with the negative moment. And then again, superpositions. You can cancel this moment, these two moments, and then you go back to the original loading conditions. So you can very cleverly, using claim and unclaimed concepts, try to move the force around. So it's not very clever things to do, plus superpositions. Okay, now how about if I have a settlement? If I have some sort of displacement associated with my structures. Now, for instance, I have this structures, and then the support A got settled downward by a certain amount. Can we solve this using moment distributions? Now, first of all, you have to realize that this point settled down, and it will induce deformations, and then you will see some curvature comes out, and it's telling you that they should have moments developed in the structures due to such a settlement. Okay, so what you can do is you can assume that to be claimed but allowed to translate vertically. Right? So this is a claim boundary condition but allowed to translate. So you can calculate, again, same thing on joint B, you also assumed it to be claimed. So then you allowed it to translate and then calculate the end moments induced by such a configurations. So you can use the slope deflection approach to calculate MAB and MBA. You just simply say that theta A is equal to 0, theta B is equal to 0. So here, both of them equal to 0. And you do have a rigid body rotations. So this is counterclockwise rotations. So you do have a value for 5 ij. And then this is fixed end moments due to loading. So this fixed end moment should be equal to 0 because there's no loadings acting on the components. So this is also 0. So the only non-zero term is rigid body rotation angle. Okay? So then you just use the concepts unclaimed, the claim assumptions. So just apply the end moments backwards, apply the end moment backwards, and then use the superpositions. You cancel these two moments, and then the only thing remains is the downward settlement at support A. Now, at this point, I want to mention that now we have been using fixed end moments in previous chapter, slope deflections, which is particularly addressing the effects due to the loading applied on the components. So here, this is a fixed end moment for chapter 11, slope deflections. Now, in this chapter, the fixed end moment takes on slightly different meanings. Now, originally, it's consistent with the previous chapter, which is due to the external loads. However, as the conditions changes, that we need to take care of also the settlement issues. So we expand the definitions of fixed end moments to these conditions. So for the moment distributions, we call this fixed end moment. So it simply implies in moment distributions that you're assuming the boundary conditions to be claimed, but you allow certain translations. So that means that the fixed end moment for chapter 12, moment distributions, is a combination of this and that. So that is a little bit confusing, but we'll try to use some example to help you understand what I mean. Okay, so summarizing the moment distributions, procedures goes like this. First, you calculate distribution factors. So you identify joints again, and then you calculate distribution factors at that particular joint. You want to distribute your moments. And then you obtain fixed end moments using slope deflection equations. And that fixed end moment could include both the effects of loading as well as settlement, which is rigid body rotation angle. And then you do the moment distributions directly, and then if necessary, you need to assume a clamp boundary conditions, and then if you need to follow further by relaxing the clamp boundary conditions, and then after you relax the boundary conditions, you need to follow so-called distributions, moment distributions, using distribution factors. Now, after you distribute into the component, then you just carry over to the other sides of the component. So carry over. And then you probably need to repeat 3 and 4 if necessary. And then at the end of the day, just sum up everything that you calculated above. The reason for summing up is because this is basically a superposition concept. It's a superposition concept. So that's why everything needs to be summing up. Okay, so let me illustrate very quickly using this example. I will illustrate more on the board. Usually we calculate moment distributions using a table format. So this is, each textbook has a slightly different versions of moment distributions format. This is the format I like to use. So here, this line is indicating joint. So this is joint B, this is joint C, and this is joint A. And then I put the first row there. The first row is distribution factors. So that is very, very first step. So you look at the 3 joints. This is A, B, and C. A, you have nothing to distribute because they only have one component. So no distribution factors. Joint B, you need to distribute between BA and BC. So you do have distribution factors there. C, again, only one component, so you don't need to worry about the distribution factors. Now, how do you obtain distribution factors? Why this is 3/7, this is 4/7? Because the stiffness coefficient here is 3EI over L, and the stiffness coefficient here is 4EI over L. So that gives you 3/7 and 4/7 if the material properties are identical and the length are identical. Right? If they are not the same, then you have different distribution. Okay, what is the first step? First step is trying to convert the loading to the joint. So the very first step is calculating fixed end moment. So fixed end moment, of course, A and B, they are not fixed ends, so you need to assume. You need to assume that they are claimed conditions in order to have this loading converted into the end moment. So this load is applied at the midspan. So if you follow the slope deflections, it's appearing at the last term. So the last term, I say you have 2 fixed end moment. You need to memorize concentrate load at the midspan, which give you PL over 8. Distribute force is WL squared over 12. So this is PL over 8. PL over 8 give you 0.125 PL. Alright, so this is a fixed end moments that you calculated using slope deflections. Here, all the others are equal to 0, only have this loading effects there. 0.15. Now the second step is you realize that you have used the claim assumptions at joint A and joint B. So what you need to do, you need to balance that. You need to apply a negative moment, right? Negative moment. Try to cancel that. and then also negative moments here. Try to cancel that. Now, the negative moment here is very easy. You just apply the negative magnitude here and then put it down, right? Because there's no distributions, no joints, no other components to share that moment. But this moment, there needs to be shared between the two components, VA and VC. So this is negative 0.125, need to balance by 0.125 in order to cancel. But this balance moments need to be distributed into the two components, following the distribution factors of 3/7 and 4/7. Okay, here. So I'm taking 0.125 multiply 3/7, 0.125 multiply 4/7, and then put it here, respectively. So this is called balance and distribute. So after you moment distribute it, then you need to look at the other side of the components. That's called carryover. So carryover. So now I have obtained the moment here. This is the moment there. Do I need to carry over a moment to the other side? Well, again, look at the far side. The far side is not moment free. It's not claimed. So it's between moment free and claim. So what you need to do is you need to assume a claim boundary conditions in order to let it carry over and then try to balance that. So what you do is you carry over by 1/2. If this is a claim boundary conditions, so you take that, multiply by 0.5, and then you remember that this is a assumed claim boundary conditions, so you do need to balance that. So that's component AB. Now, component BC, whatever you obtain here, you need to carry over to the claim boundary conditions. The coefficient you need to multiply is 0.5. So I just multiply 0.5 and put it there. Okay, so we identify that there's a balance moment that we need to distribute. So you further distribute according to the distribution factors. And then you need to carry over. So I'm looping 3 and 4. I'm looping 3 and 4. The reason why I need to loop is because I have adopted some sort of claim boundary conditions, so that I need to balance that and distribute. Okay, so I further carry over 1/2 to the other side, and then it seems that I don't have, I have not involved any further claim boundary conditions, assumed claim boundary condition anymore. So the calculations then can be stopped. I don't see this balance moment I need to distribute. So then stop. After you stop, you just do summations. Again, the reason why you need to sum up is because all of these are the results of superpositions. Right, so you summarize, sum up, and A, no moment. Moment free, no moment. Correct. BA, this is moment BA, minus 0.107. And then sum up, 0.107. Well, they cancel out because moment equidistant at joint B. If you don't have this canceled, that means that you have something wrong in your calculations. All right, so this is a claim N. So the claim N sum up 0.054. And then you take everything multiplied by PL. So these will be the N moments at A, BA, BC, and at CB. So you see the calculations goes like that, and you don't have to solve equilibrium, simultaneous equations. All you do is simple multiplications, additions, but you have to be very, very clear about each and every step of it in order to use this very calculation efficient methods. Okay, so you have to understand every one of them in order to use this methods. Okay, that's the end of this part. So to get it going, it took me 40 minutes.